explains how the EDM instrument works. The topics covered in this video include the EDMI schematic diagram and its components, the amplitude modulation process, the electromagnetic energy wavelength, and the resolution of several modulation frequencies to display the distance measured. Here is the EDMI schematic diagram. As you can see, it includes several components in the diagram, starting with the transmitter through the system clear to the display and the frequency generator. The transmitter uses a gallium arsenide diode that emits amplitude modulated infrared light. A crystal oscillator controls the frequency of the amplitude modulation. Now, what is amplitude modulation? Well, it's a pulsation of light that passes through the instrument. It's similar to passing light through a stovepipe in which a damper plate is spinning at a precisely controlled frequency. We can see in the sketch here that there is a stovepipe with a damper installed in the middle of the pipe. It is a circular pipe, and we can see that when the damper is closed, no light gets through. As soon as this damper opens up to 90 or 270 degrees, the maximum amount of light can go through, and in between 0 and 90 degrees, we have increasing amount of light coming through the stovepipe. So with the damper closed, no light passes and the angle remains at 0 and 180 degrees. However, when the damper open, light passes relative to the opening angle. We can see in the illustration here that as the damper opens and closes, we can see down below that we have varying amounts of light coming through the pipe. This is a pulsating light, and this is what's known as amplitude modulation. The maximum light passes when the opening angle is 90 or 270 degrees. Here we have a position where the angle is close to 90 or 270, and we can see in the sketch that we are receiving a significant amount of light, almost maximum at this angle. The light intensity variation is represented by sine waves. The sine wave looks something like this for electromagnetic energy wavelength. We can see in the sketch that when the phase angle is 0 or 180 degrees, that's when the plate was closed, the amplitude is equal to 0, or when it returns back to 0 again at 360. However, when the plate angle is open at 90 or down at 270, we have maximum amplitude of the sine wave, and that's when we have the maximum amount of light coming through the pipe. And so any place in between here, we will have a reduction or an increase in the light coming through the pipe. Now the wavelength is from 0 to 360 degrees. That's one full cycle of the wave. And so what the EDMI instrument tries to do is it tries to determine the phase angle of the light coming through the EDM instrument. So let's say that we have a phase angle of 135 degrees. We can see that at 135 degrees, we can come up to the curve and come across, and we see that we have an amplitude that's about 70% of the maximum. So at 135 degrees, that's around 70%. The EDMI instrument is going to look at a phase angle of 0.375 lambda. This 0.375 is nothing more than 135 divided by 360. It gives us 3/8, or 0.375. After the transmitter, we encounter a beam splitter in the EDMI instrument, and this divides the light into two signals, one for the external measurement and one for the internal reference beam. And so we can see at the beam splitter, we have an external beam coming and hitting a reflector, hitting a mirror, and that mirror sends this light out to a retroreflector. Reflector bounces the light back towards the instrument, and then it re-enters the instrument parallel to this reference beam right here, this internal reference beam that goes in parallel with the external beam. The variable filter reduces the internal signal intensity to that of the external signal, enabling a more accurate observation. Clearly, as this light goes through the atmosphere, it's going to degrade in strength as it's reflected back. Well, this variable filter will degrade the internal beam to a similar strength, so that way there's a much more accurate observation. The interference filter then takes the light that's passed through the atmosphere and the light that's retained in the instrument, and this interference filter just removes unwanted or unnecessary light. It's almost like removing background noise in the signal. And the most common background noise is sunlight coming in from the external beam. Then we encounter the receiver optics and the phase difference circuits. At this particular point, we have the internal beam and the reference beam. This is where the phase difference is determined. This converts the electromagnetic energy to electrical energy and conserving the phase shift. Once that phase shift is conserved, we go to the phase meter. This phase meter converts the phase difference into direct current, with magnitude proportional to the differential phase. And then this direct current is sent to the display. There's a null meter. It's adjusted to null the current, convert it to a distance, and display the result. And the measurement thus is made. What we haven't talked about is this frequency generator, and the frequency generator actually allows the instrument to transmit different modulation frequencies to resolve the ambiguous number of full cycles a wave has undergone. This wave, as it goes out through the atmosphere, is going to go through many cycles, or most likely several cycles, maybe only a partial cycle, but we don't know exactly how many cycles it's gone through. All we know is what's the phase shift in that particular wave. And so what we want to know is how can we take that information and resolve this ambiguous number of full cycles the wave has undergone? Well, we can explain that by an example. We have resolved a distance on the display, and just say the display is reading at a distance of 1598.324 meters. Well, how does the instrument determine that distance? Well, there's 4 channels of waves coming through the instrument. Here are the necessary frequencies to generate the related wavelength. So a wavelength of 10 meters needs a frequency of 14.984 megahertz. A wavelength of 100 meters needs 1.4984 megahertz, and so on. And so the frequency is not so much important. What's important is to realize that in the first channel of the frequency generator, we generate a wavelength of 10 meters. The second channel generates a wavelength of 100 meters. The third generates a wavelength of 1,000 meters. And the fourth channel generates a wavelength of 10,000 meters. When we go through the phase shift and read the phase shift in the first generated channel, each channel takes its turn. So the first channel generates a 10-meter wave and sends it out to the atmosphere, and it comes back. And what the instrument reads is that phase shift in the angle. We'll say the phase shift was 0.8324 lambda. Well, then the distance is nothing more than lambda times the wavelength, which is 8.324 meters. So the display will read 8.324 meters initially. Once we then send out the second channel, the second wavelength is sent out, and that wavelength of 100 meters, let's say in this particular case then that phase shift was 9832, almost a full wavelength. Well, the distance measured was 98.32 meters. The display then picks up an additional digit here. Notice that the 9832 has 3 common digits with the F1 channel distance of 8.324. These 8, 3, and 2 just verify that these first 3 digits in fact are correct, and that the 9 now is added to the display. Once that 9 is added to the display, then the EDM will send out the 1,000 meter wavelength, come back to the instrument. The instrument will determine that the phase shift was 0.5983. That means it was 59% of the 1,000 meter wavelength was resolved. That means that a distance of 598.3 was measured through the 1,000 foot wavelength. So the additional digit that we see is a 5. Notice the 983 just confirms the first 3 digits of the previous channel measurement. And so a 5 is added to the display. And then finally, the 10,000 meter wave is issued or sent out from the EDMI. And coming back, the phase shift in this particular example had to have been 0.1598 lambda, or 1,598 meters in the 10,000 meter wavelength. And so what that does is add the digit 1. Notice the 598 just verifies the first 3 digits of the previous measurement in channel F3. And so the final distance is 1,598.324. And that's how the EDM instrument makes a measurement. So in summary, the topics we've covered in this video is the EDMI schematic diagram and its components, the amplitude modulation process, the electromagnetic energy wavelength, and the resolution of several modulation frequencies to give the distance measurement. The outcome that we hope you take away from this video is that you have an understanding, a basic understanding of how the EDMI works. This ends the video lesson.